In this video, we introduce the normal distribution, also known as the Gaussian distribution. This is the most important continuous distribution in statistics and appears throughout science, engineering, and the social sciences. Many of the inferential tools you will learn, such as confidence intervals, hypothesis tests, and regression methods, are built on the normal model. Because of its mathematical properties and its frequent appearance in real data, the normal distribution plays a central role in statistical reasoning. Here we describe the basic shape of a normal distribution. If a random variable follows a normal distribution with parameters mu and sigma, its density curve is symmetric about mu, bell-shaped and continuous across the real line. One important consequence of symmetry is that the mean, median, and mode are all equal to mu. The single-peaked balance shape is what gives the normal distribution its familiar appearance. Let's highlight several key visual features of the normal curve. The curve has a single peak at the mean. The tails extend infinitely in both directions, getting closer and closer to the horizontal axis but never touching it. While any real number is theoretically possible, values far from the mean have very small probability density. This helps explain why extreme observations are rare but still possible under a normal model. Now we examine the parameter mu. This is called the location parameter because it determines where the center of the distribution lies. It represents both the balance point and the peak of the curve. Changing mu simply shifts the entire normal curve left or right along the horizontal axis without changing its overall shape. Next, we consider the parameter sigma, which is the scale parameter and also the standard deviation. This value controls how spread out the distribution is. A larger sigma produces a wider and flatter bell, indicating more variability. A smaller sigma produces a narrower and taller bell, indicating less variability. Together, mu and sigma completely determine the normal distribution. Here we visualize several normal curves with different values of mu and sigma. Notice how changing mu shifts the curve horizontally, while changing sigma changes the width and height of the bell. Seeing these curves together helps reinforce how each parameter influences the shape and position of the distribution. Here we present the probability density function for the normal distribution. Although the formula looks complicated, its purpose is simply to generate the familiar bell-shaped curve and ensure that the total area under the curve equals 1. In practice, you usually do not need to memorize this formula. What matters most are the qualitative properties of the normal distribution: its symmetry, unimodality, and smooth tails. Why does the normal distribution matter so much? One key reason is that many natural phenomena are approximately normal. Measurements like adult heights, instrument errors, and many biological traits often follow a bell-shaped pattern. This typically happens because the observed value is the result of many small independent influences acting together. When no single factor dominates, the combined effect tends to look normal. Another major reason is the central limit theorem. This remarkable result tells us that sample means tend to follow an approximately normal distribution as the sample size increase even if the original population is not normal. This is incredibly powerful because it allows statisticians to use normal-based methods in a wide variety of situations. We will study the central limit theorem in more detail in a later video. A third reason for the importance of the normal distribution is that many classical statistical procedures rely on it. Methods such as z-tests, many confidence intervals, regression inference, and quality control techniques are derived under normal assumptions or justified by the central limit theorem. The mathematical tractability of the normal model makes it especially useful for building statistical theory. Finally, the normal distribution serves as a benchmark model. Real-world data are rarely perfectly normal, but the normal curve provides a valuable reference point. Analysts often compare data to a normal distribution to assess symmetry, detect skewness, or identify heavy tails. Even when the normal model is not a perfect fit, it often provides a useful first approximation and a foundation for more advanced methods.